This video is starting the last major lesson of the semester. There are still a few more lessons to come after this one, but they're definitely not as intense or heavily weighted on the AP test. This is a topic that is definitely going to be tested on the AP test, probably in the multiple choice section, maybe like 1 or 2 questions, and then almost guaranteed to be in the free response section in some respect. It's a very heavily tested topic in the free response section. So we are going to look at solving differential equations in slope fields. This actually happens to be a huge topic in calculus just to begin with. There is a class in college. If you're a math major in college, you'll take a class called Differential Equations. And so it is dedicated to an entire semester of a college course in mathematics. But right now we'll just spend a few days talking about the introduction to solving differential equations. So, a differential equation, or in other words, an equation that's a derivative, will be in the form dy dx equals something in terms of x, or some function in terms of x, times another function in terms of y. It says in order to solve it, you must put it in the form with the functions in terms of y with the dy, and the function in terms of x with the dx. We call that separating the variables. So all the variables that have y's should be on one side, and all the variables that have x's should be on the other side. When we do that, it allows us to integrate, because now we can integrate and we only have x's on the right and we only have y's on the left. Our goal is to be able to integrate both sides in order to get an equation that is solved for y by itself, and it's a function that's just in terms of x. So, for example, here we have our first example. dy dx equals 2x over y. So notice that we have x's and y's on the right-hand side, and we have this dy and dx over here on the left-hand side. So the first thing we're going to do is we're going to separate the variables. We're going to do that by multiplying y to both sides to get rid of it over here on the right, and then multiplying dx on both sides times dx to get rid of it on the left. So if I do that, I get y dy is equal to 2x dx. Now that my variables are separated, it's in this form, where I have y times dy, and then 2x times dx, a function of y on the left and a function of x on the right. If I integrate both sides, the integral of y is y squared over 2, and the integral of 2x is 2x squared over 2, which simplifies to x squared. Now don't forget, because these are indefinite integrals, we have to have plus c. Technically, each of the integrals themselves offers up its own plus c, so there should be a plus c on the left and another constant on the right. However, a constant plus a constant is another constant. So if I have a constant over here and I just move it over here, we just combine those together, saying that it just makes one constant. So typically you'll only see the plus c appear on the right-hand side. Now our only other job is to get y by itself, because we want it in this form, y equals h of x. So if I solve for y, the first thing to do is to multiply both sides by 2. So y squared equals x squared plus c divided by 2. Or sorry, times 2, isn't it? Not divided by 2. Times 2. Notice that if I distribute the 2, I get 2x squared. If I multiply 2 times c, however, 2 times c is still a constant. So I'm not going to actually change that one. I'm just going to keep it y squared equals 2x squared plus c. Because a constant times 2 is still a constant. Maybe not the same constant, but still a constant. Then to get rid of the squared over the y, I just take the square root. So y equals plus or minus the square root of 2x squared plus c. Final answer. In future examples, we will be given an initial condition, so you'll be able to solve for the c value to find what we call a particular solution, and then also it would help us to decide if we want the positive or negative square root, just to figure out specifically which one we're looking at. But for the time being, with a general solution, we'll say that that is the general solution for this equation. All right, let's look at another example. I want to separate my variables first, so I'm going to multiply dx to both sides. And I don't want this y squared over here, so I'm going to divide both sides by y squared. When I do that, I get 1 over y squared dy on the left-hand side is equal to 1 dx. And if I integrate both sides, the integral of y squared, if I can rewrite that as the integral of y to the negative 2 dy equals the integral of 1 dx. Y to the negative 2 when you integrate becomes y to the negative 1 over negative 1. And then the integral of 1 dx is just x plus c. If I want to solve for y, I can do so by multiplying both sides by this -1. So I get y to the -1 equals, if I multiply the right-hand side by -1, I get negative x, and then technically, again, this changes to a minus c, but because I don't care if it's plus or minus, it's just a constant, I'm just going to leave it as c. So negative x plus c. And then I'm going to rewrite y to the -1 as 1 over y equals negative x plus c. And there's a short way of doing this, and then there's a long way of doing it. The long way of doing it is multiplying y over here to the right-hand side to get it out of the denominator, and then dividing by negative x plus c to the left-hand side so that it goes into this denominator. And then that's how you get y by itself. The shortcut way of doing it, which is going to happen anyway, is if you ever have a reciprocal like this, or if you ever have a fraction like this, 1 over y, and you want to find its reciprocal, as long as you take the reciprocal of both sides, the entirety of both sides, then it's the same thing. So I'm going to go ahead and do that now. The reciprocal of 1 over y is y. The reciprocal of negative x plus c is 1 over negative x plus c. And again, that would have come from if you had done it the long way as well. If you had multiplied by y and then divided by negative x plus c, you would have gotten the same answer. So again, this is called a general solution. If I had an initial condition, I could have found a specific solution. Here's another one. Divide by y, multiply by dx, multiply by dx. So we get 1 over y dy is equal to x dx. And we'll integrate both sides. By the way, notice the equations that are coming from these. So in the last ones, it was a rational equation. 1 over negative x plus c was a rational equation. In the one before that, it was a radical equation with a square root in it. So notice that the original equations we're getting from these derivatives are some of the functions we're familiar with working with. So the integral of 1 over y. Remember, this is not the one where we rewrite this as y to the -1 and then integrate, because if you bumped up the -1 by 1, you would get y to the 0 over 0, and that doesn't make sense. So remember, the integral of 1 over y is actually ln of the absolute value of y. The integral of x is x squared over 2 plus c. Now, you may or may not be familiar with how to isolate y in this example, but remember, to get rid of a natural logarithm, we can raise both sides with e to that power. So e and ln cancel each other out because log base e. So the absolute value of y is equal to excuse me, e to the x squared over 2 plus c, and all of that is in the exponent. Now, we need to have a little mini properties of exponents really quick lesson to make sure that you guys are clear on where this next step is going to come from. So over here in the corner, I want to make sure you guys are familiar with this. If I have x to the power of 2 times x to the power of 3, that's the same thing as x to the power of 2 plus 3, which is x to the 5th power. The opposite is also true. If I have x to the power of 5 plus, a, that's the same thing as x to the power of 5 times x to the power of a. I can split it back up. So if I'm adding things in the exponent, I can split it back up into multiplying like that. So here's what I'm going to do with this. Take this and restart it up here. We have the absolute value of y is equal to, here I have e to the power of x squared over 2 plus c. So since I'm adding things in the exponent, I can split that up into two different factors like this. So similarly to how I did this one, if I was adding two things, I could do x to the 5th times x to the 9th, or x to the a, I mean. So in this case, we have e to the x squared over 2 plus c is the same thing as e to the x squared over 2 times e to the c, because we can just add those exponents back together again. Now, keep in mind that e to the c is just a constant. E is a number, and c was a constant. So e to a constant is another constant. I'm going to just make it a k instead of another c, just because that's how you'll typically see it. So we have the absolute value of y equals e to the x squared over 2 times k, and typically they'll write it in front. Sorry, 1 second. Sorry, the dogs go kind of crazy when somebody comes to the door. So I'm just going to rewrite this with k in front. So k e to the x squared over 2 is equal to the absolute value of y. Now, from this point, to get rid of the absolute value, we would have an initial condition, so we could actually solve for whether or not it's like the absolute value is going to affect the function. But in this case, because we don't have an initial condition, we'll just say that if we want to isolate y, remember that an absolute value function takes positive numbers and keeps them positive, and then it takes negative numbers and makes them positive. So depending on what k is, this could be a positive number already, and the absolute value would have nothing, like it would have no effect on the equation. Or if k made this a negative value, then the absolute value, of course, would make it positive. So because we don't know which one it is, we're just going to put plus or minus k e to the x squared over 2. Just because we don't know, like I said, we don't know if that absolute value is necessary or not, so we'll just put plus or minus until we come up with an initial condition to figure out what that absolute value is. And there's our final answer. All right. So this is the last one we're going to look at today before we jump into some for tomorrow. Excuse me. It says, and these are the steps, by the way, the ones we've been talking about, except this time I'm giving you an initial condition. So I wanted to write down the steps now so you guys could see how it works. So the steps to finding a particular solution. So far with the examples that we've done, we've only been finding what we call a general solution. And now we're going to go ahead and find a particular solution. So it says step 1, to separate the variables. By the way, if this is in the free response section, if you do not separate the variables, you don't earn any points. They literally put that on every single one. It says if there is no separation of variables, it is 0 points. So obviously this is the most important thing. That's the only way we know how to solve these equations now, is to separate the variables. So let's do that first. We already have e to the x over here on the right-hand side, and we have y on the left-hand side. My dy is on the left-hand side, which is perfect. I need to move dx over to the right-hand side. So I'm going to go ahead and do that by multiplying it over. So y dy is equal to e to the x dx. Check. Step 2, integrate both sides, and don't forget about adding plus c. So integrate the left, integrate the right. On the left, that becomes y squared over 2. On the right, the integral of e to the x is itself, e to the x plus c. They usually give you points for adding plus c, so if you remember to put that plus c, you can earn some points for that. It says use the initial condition to solve for c, and then substitute it back into the general equation. So here's my initial condition. Y of 0 equals 4. So everywhere I see an x, I'm going to plug in 0. Everywhere I see a y, I'll plug in 4. And then c is what I'm solving for. So 4 squared over 2 equals e to the 0 plus c. 4 squared is 16. 16 over 2 is 8. So 8 equals e to the 0, which is 1, plus c. Therefore, c is equal to 8 minus 1, which is 7. So my particular solution, I haven't solved for y yet, but my particular solution with c in it is y squared over 2 equals e to the x plus 7. Next step is to, you guys can't see it down here, shoot. Solve for y in the general equation. All right, so now we have our specific, this is our specific equation now. So we're going to solve for y in our specific equation. So multiply 2 over to the other side. So we get y squared equals 2e to the x plus 14. So again, I just multiply by 2 over to this side. And then to get rid of that squared, we put y equals plus or minus the square root of 2e to the x plus 14. Now, because we actually have our initial condition in this case, we are able to actually determine one or the other. So this is actually not plus or minus. We can decide on which one it should actually be. Because my initial condition says that when I plug in 0, I should get a positive 4, let's see which one it should be. If I plug in 0 here, I get e to the 0, which is 1. 1 times 2, which is 2. 2 plus 14, which is 16, and the square root of 16, which is 4. And if I want it to be a positive 4, then I should keep the positive square root, not the negative one. So my final answer is y equals the positive square root of 2e to the x plus 14. So notice that at that very end point, you have to make a decision on, I don't want to keep both of these plus and minus, I just want to know which one I need in order to get my initial condition back out, and that would be the positive square root. Perfect. So that was our last example of looking at solving differential equations. I do want to look at one more thing before we get into tomorrow's lesson, because so far these are just examples, and I want to show you guys how it appears on the AP test. And so on the AP test, it appears in its entirety with one more thing attached to it. So I want to talk about that one more thing as well. And that one more thing I want to talk about is called slope fields. So I want to show you guys how to do number 3, and then I will pause the video while you guys attempt number 4, and then I'll put the answer up there so you guys can see it. So essentially what a slope field is that it gives us an image, or it gives us a picture of what the particular solution, or actually I guess it's a bunch of general solutions, what the general solution could look like depending on the slopes at individual points. So I know this is going to seem like a lot of work. There's a ton of work. The AP test doesn't have you do this many, but just for the sake of practicing, we'll do them all. So essentially we're going to plug in these points. So for x equals 3, y equals negative 3, we're going to plug it into our differential equation and see what the slope is. And then on our coordinate grid down here, we're going to try our very, very, very best to draw a little teeny tiny line that has a slope approximately what we think it should equal. So let's get started. For this first one, I'm plugging in 3 for x and negative 3 for y. So if I plug that in here, I'll try to write it a couple times. I won't write it every single time, but I'll try to write it a couple times for us. If I plug it in here, that would be negative 3 over negative 3, which is 1. Let's do all the diagonals first, because I want to be easy on myself. If I plug in 2 and negative 2, that would be negative 2 over negative 2, which is 1. If I plug in 1 for x and negative 1 for y, that would be negative 1 over negative 1, which is 1. All right, I'll write one more of them down, I guess. We'll go across this way now. If I plug in 3 for x and negative 2 for y, that would be negative 3 over negative 2, which is 3 halves. So I'm going to stop writing the work in there. I'm just going to write the equation now, or the answer, I should say. If I plug in 3 and negative 1, that would be negative 3 over negative 1. That's positive 3. If I plug in 3 and 0, that would be negative 3 over 0, which is undefined. Notice, by the way, that when y is equal to 0, these are all going to be undefined. So let me put those there. Undefined, 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 undefined. Perfect. And also, when x is equal to 0, if I plug 0 into the top of the fraction, I'm going to get 0 over another number, which is 0. So I'm going to go ahead and fill all those in now. Those are patterns that we can notice. I'll plug in 0 there. All right, perfect. Now let's get back to it. If I plug in 3 and 1, that would be negative 3 over positive 1. That's negative 3. 3 and 2 would be negative 3 over positive 2. That's negative 3 halves. 3 and 3 would be negative 3 over 3. That's negative 1. All right. 2 and negative 3 would give me a negative 2 on top and a negative 3 on the bottom. That's 2/3. All right, and this next one right here. If I plug in 2 in the top and negative 1 in the bottom, that would be negative 2 over negative 1, which is positive 2. If I plug in 2 on top and 1 on bottom, that would be negative 2 over 1, which is negative 2. 2 on top, 2 on bottom would be negative 2 over 2, that's negative 1. And 2 on top, 3 on bottom, that would be negative 2 over 3, negative 2/3. All right, perfect. Why don't we do this? I didn't realize how much work it was to fill in one of these charts. So why don't we nix number 4? I'm going to nix number 4 and say we don't have to do number 4. And we'll just do number 3 together, but I'm going to actually pause here and we're going to fill in the rest of the chart on our own. So I'm going to pause the video, and when I come back, this whole chart is going to be filled in. So I want you guys to pause the video and try to fill in the rest of the chart on your own. Make sure that you know how to do it. How about this? We'll do one row at a time. So I'll do a row and then I'll unpause it for you to check. And then I'll do another row and I'll unpause it for you to check. That way we can do it a little bit quicker and you don't have to sit here and listen to me talk. So go ahead and fill in one row at a time and then unpause it to check the work. All right, so here's that first row. 1/3, 1/2, 1, undefined, -1, -1/2, -1/3. All right, pause the video again, and then unpause it when you're ready to check the row for -1. Here's the row for -1. We get -1/3, -1/2, -1, undefined, 1, 1/2, 1/3. All right, pause the video again to check the next row. All right, for this row, we get -2/3, -1, -2, undefined, 2, 1, 2/3. And pause it one more time to check the last row. All right, here's the last row. So, again, for the row -3, we get -1, -3/2, -3, undefined, 3, 3/2, and 1. Perfect. So here's what we're going to do. We're going to come down here to our grid, and we're going to plot a little teeny tiny line that has these slopes at all of these different points. So we'll start over here in the corner at, this is x equals 3, y equals -3. So we'll start right here. So at x equals 3, y equals -3, it says that the slope field has a slope of 1. So I'm going to just draw a little teeny tiny line about yay high. Notice that it has a positive slope, and I'm going to estimate that slope is about 1. Now the next point is 3, -2 on the y-axis. So 3, -2 is the one right above it, and it says it has a slope of 3/2. Well, 3/2 is a little bit more than 1, so I'm going to try and draw it just a little bit steeper. And the next one, at 3, -1, it says it has a slope of 3. So 3 is a pretty steep line. So right above that, I'm going to draw one that has even steeper slope. So that's my best estimate at a little tiny line that has a slope of 1, a slope of 3/2, and a slope of 3. The next one is undefined. Remember that an undefined slope is a vertical tangent line, so I'm just going to draw a line straight up and down. Then up here, it goes -3, -3/2, and -1. So -3 would be a pretty steep line, but facing backwards. -3/2 is a little less steep, but still facing backwards. And -1 would be the flattest of them and facing backwards. For the next line, we get at 2, -3, which is this point right here, we have a slope of 2/3. So 2/3 is a little bit less than 1. So it should look kind of like this one, but not as steep. All right, there we go, 2/3. Then a slope of 1 and a slope of 2. So here's my slope of 1, here's my slope of 2. Undefined goes straight up and down. Then we have -2, -1, -2/3. So -2 is backwards, but kind of steep. -1 goes a little bit flatter, and then -2/3 goes a little bit flatter. They don't have to be perfect, by the way. All right, the next row is 1/3, 1/2, 1. So 1/3, pretty flat. 1/2, a little steeper. 1, a little steeper. Undefined. Then it goes -1, -1/2, -1/3. So -1, -1/2, -1/3. All right, this next row is all 0, 0, 0, and then undefined, and then 0, 0, 0. So 0, 0, 0. Undefined is straight up and down, and then 0, 0, 0. Excuse me. The next one, so we're over here at -1, -3. So we're going here, and then we're going to go up. -1/3, -1/2, -1. So again, a negative slope, but not very steep, and then a little bit steeper, and then a little bit steeper. Then we get to undefined. And then +1, +1/2, +1/3. So +1, then a little less steep for +1/2, and a little less steep for +1/3. The next row, -2/3, -1, -2. So -2/3, -1, -2. And then undefined. Then 2, 1, 2/3. So steep, a little less steep, a little less steep. And last but not least, -1, -3/2, -3. -1, a little bit steeper for -3/2, a little bit steeper for -3. Then undefined, and then 3, 3/2, 1. So steep, a little less steep, a little less steep. Okay, that is a slope field. So we created a slope field from all of these points and plugging them into this differential equation dy dx to create an image of what the original function looks like. Now, I hope it's obvious to you what this original function is going to look like. It's kind of creating this circular pattern. So if I actually solved this differential equation, -x over y, I should get the equation of a circle. So the last part of it says find the solution going through 1, 1. So I'll do that one in red. Essentially what they want you to do is they want you to find the point 1, 1, and then they want you to do your very best, excuse me, to follow these slope field lines in order to draw an image of what it looks like. So notice that the slope field line is kind of pointing me down this way, and then once I get down to the x-axis, I see vertical slope field line, so I should probably follow the vertical line. And then once I get to here, you can see there's kind of slanting back this way. So I kind of treat it like pinball, like almost bouncing off of these little lines and kind of following the lines as best as possible. So if we follow the lines as best as possible, we get here, we get undefined, so come down. Now it's sloping backwards, so we got to slope backwards. Keep sloping backwards. And then we go horizontal, so it should be flat. Now we have some positive slopes. We get to positive slopes. Then we come over here, and then we have vertical slopes again, so undefined. Oh, now they're back here, and then flat again to connect it back to the beginning. So notice that it kind of creates this circular shape. So that was the first one. And then in green, it says to draw the same, another solution, but going through negative 2, 0. So here's negative 2, 0. I'm going to draw my best bet at it, which it won't be perfect, but it'll be something like this. Alright, so a circle going through that point. Anyway, you can see how choosing different points gives you the different graphs that you would be looking at. That's kind of how slope fields work. Like I said earlier, when we look at some of the examples tomorrow, the examples that we do won't require so many points. That would take forever on the AP test. So usually they ask you for like maybe 6 or 9 points, possibly even like 12. But you'll see some examples of that tomorrow. So that's it for today.